from where we ended. Let's continue from where we ended last time. We were talking about uh, measurements of mass and weight. We said that mass, that is on page 10, 2.4. We talk about mass is a measurement of the quantity of matter contained in a body. When you say mass is a measurement of quantity of matter contained in a body. And we say that the weight of an object is a measure of the force or the force of gravity on the object towards the earth. That's what we call it weight. So you should know, Deborah, please, mute your microphone. Deborah, mute your microphone. Okay, good. All right. Please mute your microphone unless you want to ask a question. Abdallah, Dasana, mute your microphone. Abdallah, Dasana, mute your microphone. Mute your microphone, please. Mute your microphone. All right. So I ask you to go and find about maybe 4 differences between mass and weight. And last time we mentioned about some of them, that the mass is a basic quantity, weight is a derived quantity. Can talk about that one. Mass is constant. Weight of a body varies from place to place. And you can use the definition that mass is the measurement of the quantity of matter in the body, while weight is the force of gravity on the body. I'm going to talk about the fact that the units of mass is kilogram, while that of weight is Newton. And they can talk about the instrument for measuring even mass. And mass is measured with a beam balance, or chemical balance, or total balance, or liver balance, whereas weight is measured with a spring balance, or we call it the Newtometer. Today, we want to look at dimensions and unit analysis. We want to look at dimensional analysis and unit analysis. That is session 2.5. Session 2.5. Now, let's quickly go to it. Now, if we look at the learning objectives, objective number 4, we said that using dimensional analysis to verify the correctness of an equation and units. Okay, and so here in dimensional analysis, our main focus is to use dimensional analysis to verify the correctness of equations and units. Now, I may read and then explain it bit by bit. I'm reading on the 2.5. The fundamental quantities used in physical descriptions are called dimensions. Okay, so basically when you say dimensions, you can also refer to the fundamental quantities which are used in the physical description. Okay, for example, length, time, mass are dimensions. You could measure the distance between 2 points and express it in units of meters, centimeters, or feet, but the quantity still would have dimensions of length. It is common to express dimensional quantities by bracket symbols, as maybe bracket of L, bracket of capital M, bracket of capital T for length, mass, and time. Okay, so what he's saying is that the fundamental quantities are referred to as dimensions. Instead of writing maybe dimension of time like this, okay, I can just write capital square bracket and capital T. Okay, when I say square bracket like this, then this is dimension of time. If I write a square bracket and I put M here, it is same as writing as dimension of mass. This is write a dimension or square bracket of mass. Can write this. Just square bracket of time. Okay, and then dimension of length could also be written as just capital L like this. Okay, capital L. So we use capital T in square brackets, capital M in square bracket, capital L, but to be the dimension of time, mass, and what and length. Okay. We have other quantities for the remaining FNs and basic quantities. Okay. But let's deal with only these 3 for now. Okay. So when you say dimension, it's just referring to the fact that it's referring to the units or the quantities, fundamental quantities. Okay. All right. The derived So let me go there. Derived quantities are also combination of dimensions. For example, velocity has dimension of L over what? T. Okay, so because velocity, or let's say speed, let's speed. Because speed is distance over time. Okay, or typically velocity, you can say velocity is equal to displacement over time. You can say that the dimension of velocity is called dimension of velocity or displacement over dimension of time. Similarly, you can say dimension of speed is equal to dimension of distance over dimension of what? Of time. So it's not curl bracket, it's curl bracket. So I can say that if we are using L to represent the dimension of distance or separation between the 2 points, this becomes L and this over what? Over time. Practically, if you're writing it practically, the best way to write it practically is normally writing them without the brackets. Okay. Sometimes you can also write them like this without the bracket. It's a T, just T. You put the quantity rather in square brackets, and then you can use T. Okay, some also write that the dimension of time can be like capital T dimension, but they can also bring this one. It doesn't change it. All right. Now, all right. So let's go on. For example, dimension of velocity can be L over T, or dimension of L over dimension of T. Okay. All right. Dimension of volume, because volume is length and breadth times height. Because length is the same as separation between 2 points, that's measured in distance, and breadth and height, they are all separation between 2 points. You can say dimension of volume is L times L times L, or bracket, square bracket of L is power 3. Is okay. Any equation must always be dimension consistent or homogeneous. This means that any 2 terms added or subtracted in an equation must have the same units. For example, given the equation 3.0 meters plus 2.0 meters become 5 meters. Okay. Similarly, A plus B must be equal to C. Now, what he's saying here is that when you have an equation, a set that has mathematical expression that has equal swing sign, that's the equation. When you have an equation, it can only be correct when the 2 sides of the equation are having the same dimension or same units or the same fundamental quantities. For instance, I can't say that do an expression of 5 days minus 3 mangoes. 5 days minus 3 mangoes. 5 days. Let's say 5 days. 5 days. Minus 3 mangoes. I don't think it can be done. Okay. The dimension here or the quantity here, days, here, mangoes are not the same. We cannot subtract. Okay. You can only subtract or add 2 quantities when they have the same dimension. And when you say that you have derived an equation, then it must be that the dimension of each term of the equation or the dimension of both sides of the equation must be the same. You can't say that, oh, I've done equation B. The equation is A equals B plus C. These are the equations that you have done. But you say that the units or the dimension of the quantity here is maybe days. And here the quantity here is cars. Let's say this is cars. And here is, let's say, mangoes. It can't be possible. How can this equal to what do you call it? Mangoes plus cars. This term, and this term must have the same dimension. In other words, they must have the same quantity. Or we can say even they must have the same unit before the equation can be correct. Is that okay? That's what it's saying. That any equation must, that's what I'm reading from them. Page 10, just after the volume. Okay. Any equation must always be dimensionally consistent or homogeneous. This means that any 2 terms added or subtracted in equation must have the same unit. For example, as I've said, okay. All right. Comparing both sides, we have L plus L equals L. That is the 3.0 side, 3.0 meters have units of or has units of L or dimension of L, that is length, and the 2.0 has dimension of length. So you can add length to length and you can get the 5.0 also having units of length. Okay. In other words, length plus length gives another length, not to what L. Okay. So what he's saying is that when you are doing dimension, when you have L in dimension of length, quantity length, and you are adding another quantity of length, the dimension just simply become length, not 2L. Otherwise, somebody will say that, okay, then it means that dimension of L minus dimension of L become equal to 0, not 2. You can say it's equal to 0. Okay. You just simply say that if length is derived from length, the dimension that is length also become what? Length. Okay. You don't say it's equal to 0. That's why we don't do dimension of length and dimension of length equals 2L. No, we just say that it's just length. Is that okay? It's not 2L. The above procedure, so the procedure for checking units in equation is called dimensional analysis. So you have dimensional analysis. The dimensional analysis is a procedure, okay, used to verify or check.
Hello, sir.
Yes, please.
Please, sorry, please, which units are we now? Because we just
Unit,
joined. Last
unit
week,
one,
the
unit one,
network wasn't clear, so we couldn't join.
unit one, 2.5.
Okay.
Unit one, 2.5.
Session.
Session 2.5.
Okay.
All right,
Okay. Thank you, sir.
welcome. So the procedure for checking units in equation is called dimensional analysis. So dimensional analysis is a procedure which is used to check or verify units, okay, in an equation. Okay, that's what called dimensional analysis. But dimension just refers to a physical the quantities. Okay, the basic quantities are operated as dimensions. It is formally defined as a procedure by which the dimensional consistency of an equation may be checked. It is formally. So you can also say that dimensional analysis is a procedure by which dimensional consistency of an equation may be checked. Okay. This is what is dimensional analysis. It's a procedure by which the dimensional consistency of an equation may be checked. One major advantage of dimensional analysis is its usefulness for checking whether an equation that has been derived or being used to solve a problem has the correct form. The dimensions and units of some common quantities are given below. Okay, so there are several units of there are several uses of dimensional analysis. You can use it to check the units of a quantity based on the dimension. You can define or you can find out the units of the quantity based on dimension. So you can check the validity of an equation, and then you can even use dimensional analysis to establish an equation between two or more quantities. But under this one, we are trying to look at how you check the validity or the correctness of an equation. For an equation to be correct, okay, for an equation to be correct or accepted, the dimension of each term are the same, or the dimension of whatever dimension of each side of the equation might be what? Might be the same. That's what we are saying. Is that okay? All right. Okay, so let's look at some of examples of dimension of both basic and then derived quantities. So as I said, mass, time, and length can be MLT. Area will be length times length. So the area dimension or dimension of area will become L squared. Volume can become L cube. Velocity can become L over T. Acceleration is velocity. It comes for velocity over time. Excuse me. Excuse me. Acceleration comes from time rate of change of velocity, or you can say acceleration because velocity change, okay, over time. So dimension of acceleration, some dimension of velocity, or dimension of what? Dimension of velocity is Lt minus 1. Okay? Or we call it L over T. L over T mathematically the same as Lt minus 1. And dimension of time is T. So we can say Lt minus what? 2. Right? So dimension of Lt minus 2. We put the quantity rather in the dimension brackets, maybe dimension of acceleration, then it is normally written as Lt minus 2. You can also bring the bracket, it doesn't change anything, but normally write that as this. So you can use this one to write dimension of several basic quantities based on the definition you do. For instance, force. Force is coming from mass times acceleration. Okay. So if I say what dimension of force, you can say that dimension of force, you put the force, it can become dimension of the mass. Okay, times dimension of what? Acceleration. Then mass is capital M, acceleration is Lt minus 2. So MLT minus 2 becomes the dimension for what? The force. Is okay. If I say work is coming from force times maybe displacement. From displacement. So dimension for work will give us dimension of force over time dimension of what? The displacement. So dimension of work can become force is MLT minus 2 and displacement is L. So you can get ML to T minus 2. Work and all the forms of energy have the same dimension. If I say the dimension of energy, same as work. Okay, work and energy have the same units and they have the same dimension. Is that okay? This is the dimension of pressure. You have to know pressure is force over area. So dimension of, let's say, pressure, but dimension of force, but dimension of what? Area. Force is MLT minus 2. Area is L squared. So this is L, this is L squared. 1 L cancel. So you get M T minus 2 on L. Okay, then it goes up to give us M L minus 1 T minus 2 as the dimension for what? For dimension for pressure. Okay. Dimension of power. Power is time bit of work. So if you want dimension of power, become dimension of work over time. So dimension of power, dimension of work over time. Because work is M L squared T minus 2 and time is what? T. This T will not cancel because this is minus. Okay, so this one will go up to give us minus 3. So you got ML 2 T minus what? Come dimension of power. Dimension of power. Is okay. So you can combine a lot of the units or the fundamental quantities to get a certain derived quantity dimension. Okay. Based on the dimension, you can clearly see how the fundamental quantities are related to a certain derived quantity. Okay. So for instance, if I say the dimension of power is ML squared T minus 3, number one, it tells me that in power, we have fundamental quantities like mass, length, and time. And it tells you how they are related. Okay, it is it is related to the square of what they call it, the length or distance, choose the power minus 3 a time. Is okay. So dimensional analysis will also let you know the number of fundamental quantities in a certain derived quantity. Is okay, and how they are related. Okay. These are some of the uses. I can then quickly change the quantities here to their respective units. Their respective units. For instance, I've seen that power is M L to T minus 3. I can, with this one, write the base units of power. M is for mass. Mass are units of kilogram. Okay. This is for length. Length has units of meters. You get meters squared. And this is time for seconds. Time has units of seconds. So you give S power minus 3. So this gives me what we call the base unit for power. Base unit for power. Power has SI units called watts. Capital W or small w a t, watt. But in base units, we have base unit and have SI unit. The base units for force, okay, force is force dimension M L T minus 2. Okay, T minus 2. So the base unit becomes kilogram meter per second square. It's what we call the base units of force, but the SI unit of force is called the Newton. Is okay. So in a dimensional expression, you can find or see the base unit of what the quantity, or you can easily write the base unit of the quantity. So let's see how you use dimension to check the correctness or the homogeneity, or you can see the validity of an equation. For an equation to be valid, all the other terms must have the same what dimension. So for example, 1.1. Check if the following equations are dimensionally correct. We have x is equal to 80. Okay. Obviously, they will give you what S stands for and what A stands for and what T stands for. Here, S is position. Position, or you can say displacement. Okay. A is acceleration and T is time. The dimension of position must be correct. Dimension of this side must be equal to dimension of this side and dimension of what? The T. So it's acceleration, T is time. Now, the dimension of position is length. And the dimension of acceleration is LT minus 2. What are the dimension of time, which is T? So you see that you get L is equal to LT minus 2 times T. This time it gives us, it's like T to the power minus 2 plus 1. So you get LT minus 1 equals L. Now this is not correct. It's not correct. Here has L, here has LT minus 1. The terms or the two sides of the equation that doesn't have or don't have the same dimension. So this equation is not what you can say is not it's not true, it's not valid. It's not okay. This equation is not valid. Okay, all right. Now look at the other one. You have Ax equals A T squared. Okay. Dimension of x equal dimension of A T squared. X has position or displacement has length. Acceleration has LT minus 2 and time is T, but the time here is T squared. You put the square here, so that gives us LT minus 2 times T squared. So that's it. Here is here T minus 2 and T2 will cancel. It's like become like T minus 2 plus 2. Become T is power 0. This power 0 is 1. 1 times L gives us L. So this here, the dimension of this side and this side out are the same. Okay, so this equation is dimensionally valid. This is not valid. Okay, so if somebody come and tell you that, oh, I have derived an equation between position, acceleration, and time, and say this is the equation. Okay, how will you determine the equation can be correct or not? First, it doesn't pass the dimension test, and the equation is correct. It's not correct. Okay, so once S and this is not dimension correct, okay, it means that this equation cannot be a scientific equation. It's not correct. This one can be because it has passed the first law, that the dimension of both sides are the same. Okay, that's how we use dimension. Let me go back. Let me go on there. This equation is dimensionally correct, but as you will see later, it is not physically correct. So an equation can be dimensionally correct, but not physically correct. The actual equation is that you bring a half. The actual mathematical equation that you bring a half. Okay. So some equations can be dimensionally correct, but not physically what? Correct. Okay. All right. The half has no dimension. So when you add, if I give you this equation like this, and I say that find the dimension and check whether the equation is dimension correct, you will not include half. Okay, you just say that in dimension of x equals, then you can even put the half in dimension box, and put the 8 dimension box, and put the t square dimension box. And then you see that, but half has no dimension, half has no units, not a quantity. Okay. So when I'm writing the dimension of both sides, and I say that L is, if the dimension position is L, this will not come again. Then to let it a t minus 2 times t squared dimension. Okay. And that's what it should be. All right. So when you are dimension analysis, you check the value of equation, and there is a value there, a value maybe 2 pi or pi. They are all dimensionless. They will not have any dimension. Half 3 pi, they don't have dimension. Some constants of equation don't have dimension, but some have dimension. Bear in mind. Okay. All right. Let's look at okay. Units. Okay, look at the sentence here. The fraction half has no dimension, and it's a dimensional number. Now, doing dimensional analysis with the symbol is fine, but in practice, it's often more convenient to use actual units abbreviations such as meters, second, and kilogram. Units can be also treated as symbols and cancelled. Using units instead of dimensional, using units instead of the symbols in dimensional analysis is called unit analysis. Okay, so I can use also unit. Unit of displacement is meters. If acceleration is meter per second square. This of time is what? Second. Become unit analysis. Now that become unit analysis. Right. So let's look at the questions that are there. Let's look at so some of them I'll leave you to go and look at it. But let's go to question 3. That says self-assessment question exercise 1.2. Let's look at the question 3. Let me take you to the question 3 and move on. Question 3 says that if you are there, unit assessment exercise 1.2. Question 3. It says that the Newton's law of universal gravitation is represented by F equals capital G, capital M, small m, all over R squared, where F is the magnitude of the gravitational force exerted between one small body on another. M and capital N and small m are the masses of the objects, and R the distance, F is the force. SI unit is kilogram meter per second square. What is the SI unit of the gravitational constant G? Capital constant G. Okay. All right. So here it's just telling you that there is a mathematical formula for the gravitational force. Okay. Newton said that if you have a very big object, let's call the mass M, capital M, and a small object, small mass M. And the distance between them is, let's say, R. Then there's a force of attraction between them. Which means say that the value of the force of attraction is equal to, or first he said it is proportional to the product of the masses, and then inversely to the square of the distance between them. When you introduce a constant, that constant, if you want to take the percentage away and bring a constant, and bring it close, you must introduce the constant. That constant is G. So M small m over R squared. That constant is called the universal gravitational constant. Now, our question says that what is the SI unit of the proportionality constant G? So here we need to make James habits. Okay? So from here, we make James habits. Okay. So we make it James habits. Let's go multiply by F at R squared. We get F times R squared is equal to G small capital M small m. The next step we divide through by M small m, M small m. This and this cancel. We have G is equal to F R squared over capital M. So this is the equation for the gravitational constant G, the proportionality, because F R squared over capital M. Now, they have given you the units, okay? The SI unit of force is kilogram meter per second square. So if I'm doing unit analysis, this force is kilogram meter meter per second square for this. Now, this R is distance. Distance has units of meters. So R square will give us meters square. And then mass has units of kilogram. So this mass will be in kilogram. This mass will also be in kilogram. And then you can see that I'm doing unit analysis. Let me keep this one. From this is not equal to this. If the units of this, the units of this is equal to this. The units or dimension of this. Now, this will cancel this. Okay, this will cancel this. And this one is m to the power 1, m to the power 3. 2 will become m to the power 3. So I'll get m to the power 3 because of this and this multiply. Then I've got kg is equal to negative 1. And s is equal to negative. Then comes the SI units for the positive first, the smaller negative, then the last negatives to come. Okay. How would that become? In terms of dimensional, not unit analysis, but in the meta analysis, I would have written L3 M minus 1 T minus 1. In terms of dimensional analysis, I would have written this. In the unit analysis, becomes the sequence we should find the SI units, so that will become what this. Okay. We just make general subject and put the respective units in the equation. It's okay, and then so for the one that you're supposed to have. So that is how we did. Go and try hands on the question form. It's just similar like the one you have done. Just that the half will not be a dimensional value. So when you take the dimension, the half will not come again. Okay, so you have dimension of the position x is equals to the dimension of a, the dimension of t squared. So there are so many of them. You just have to look at some of the past questions and then go through and see how you solve. Let's quickly look at the section 3. Section 3. Vectors and scalars and components of a vector. Components of a vector. Let's quickly look at that one. So I'm reading the intro of Unit 1, Section 3. All physical quantities can be grouped into scalars and vectors. In physics, scalars and vectors are used to explain concepts. Mass, distance, speed, examples of scalars. So mass, distance, speed, examples of scalars. Displacement, velocity, acceleration, and the force, examples of vectors. So basically, you should know about 3 of them. Okay. Also, this session teaches you how to break a given vector into its components. A vector lying in the xy plane and directed at an angle has both x component and y component. How to determine magnitude and direction of vectors are also discussed. So, learning objectives. At the end of this session, you should be able to 1. Explain scalars, give examples. Explain vectors and give examples. Distinguish between a scalar and a vector. Components of a given vector. You have to write the components of a given vector. We shall look at what are components, and then magnitude of vectors and direction of what of vectors. So let's cut vectors and scalars. So as the intro says, emphasis physical quantities can be grouped into scalars and vectors. Okay. Not all quantities involve direction. A scalar quantity is specified by a single value with an appropriate unit and has no direction. That is, scalar quantities has no magnitude, has only magnitude but no direction. Okay. Physical quantities like temperature, volume, mass, time, intervals, pressure, and energy are examples of scalars because they have only magnitude with units. Okay, so energy is a scalar. Don't forget, energy is a scalar. Work is a scalar. A minute, let me bring a chair. All energies are scalars. You can simply add scalars without considering any direction. Okay. If I see the ages of 2 boys, if one is 6 and another is 5, what are the ages? Some of the ages 6 plus 5, 11. I didn't consider direction. But if I say two forces are acting on the body, one is 6, one is 5, what is the sum of these forces? The direction is very important. If one force was going this way on the body, another force was going this way on the body, then if here is 6 and here is 5, there will be a net of 6 minus 5. Now I'm giving us what? Like a body going this way with 1 Newton. If both forces were going this way, 6 and this is 5, they would have given us a body being acted upon by 11 Newton. Somebody is applying a force, two forces here. If 6 Newton and 5 Newton, 5 Newton this way, the effect you get on the body will be different from when they are acting this way. I hope it's this basic science, which basic understanding. Okay. And even if they are acting this way, one is coming this way, the body, one is coming this way, the effect you get will be different. Okay, because their directions matter. Okay, the very directions matter. They are what call vectors. The directions are very important. Okay, they carry their effect alongside with their direction. So their direction has a major role to play in their effect. Okay, so such quantities are what we call vectors. Okay, those that don't have those in which their direction have no meaningful role in an addition or subtraction are called scalars. Okay. So we say that vectors, or you can say scalars, our quantities have only magnitude but no direction. Example of them: energy, work, pressure, mass, length, time. Okay, these are volume, area. These are all what we call scalars. Let's connect this. The vector quantity has magnitude as well as direction. It is typically represented by an arrow whose direction is the same as that of the quantity and whose length is proportional to the quantity's magnitude. What is said that we represent a vector by a straight line having an arrow on it. Okay, the direction of the vector is indicated by the arrow, or is determined by the arrow. So this one, the direction of the vector is going this way. Now the magnitude, okay, the quantity of that vector is proportional to the length, okay, of the line. If I write or I draw two vectors this way, okay, and I say, what can you say about vector A and vector B? Okay, one, they have the same direction, but in vectors, the one with the longer line, say, has a higher magnitude. Okay, so if I draw this and this, so I can't draw this and call it 4 Newton, and I call this one 3 Newton. The diagram, which is wrong, scientifically wrong. You can't draw this because 4 is bigger than 3. We expect the line of the 4 should be bigger than the line of the 3. So here should have been 4 Newton, and here we have 3 Newton. Okay. So that's what we are seeing today. See that the direction of the vector, so that's what I'm saying, that it is typically represented by an arrow whose direction is the same as that of the quantity and whose length is proportional to the quantity's magnitude. The direction of a vector is often expressed as an anti-clockwise angle of rotation of the vector about its state, starting from the due east. Normally, in vectors, we measure the vectors from due east, this east, west, south, north. We measure here and go in this direction, anti-clockwise. Okay? So this is 40 degrees. So if I say that a vector is inclined at 40 degrees, this is 40 degrees, okay? Or I say vectors have a direction of 0, 4, 0. It means from here going in this direction. In this direction. Not here. Not here. It becomes 0, 4, 0. And if I say the vector has a direction or a bearing of 120, it means that starting from the east, here is 90, and then here becomes 90 plus 30. So this comes from 120. But a vector is on a bearing of 120 degrees. And then it's from the east, in the anti-clockwise direction. Is that okay? Now, instead of saying bearing of, let's go back small. Instead of saying that it's on a bearing of, let's say, 0, let's say 040 degrees. Okay, 040. If I say the vector is on a bearing of 040 degrees, like this, means going this way. This one can also be same as 40 degrees north of what? Of east. The northern part of east. What is not north of east? But 40 degrees northeast is different. Okay, that is north, and you go to this here, that become the 40. This is east of north, north of the east. That be the northern part of the east. It's okay. But this is 40 degrees northeast. 40 degrees north, then you go to east. So these two are different. Okay, you should know how this is related. All right. So let's really go on. Using the conversion, a vector E with a direction 40 degrees is a vector that has been rotated 40 degrees in the anticlockwise direction relative to the due east, as shown in figure 1.1. Okay, so the next figure is in the next picture. You see this picture. Okay, a vector E with 40 degrees this way, north, and then east, west, and then north, south. Now let's go on. Examples of vector quantities are displacement, velocity, acceleration. Is also at least no 3 of the vectors, no 3 of the scalars. All right. Now, what do you mean by components of a vector? Component of a vector. Okay. If a vector is going like this, it has moved somehow along the east side, and has also moved somehow at the north side. Okay. Now, the effective value of the vector, let me take the vector A so that it doesn't confuse us with the E. The effective value of a vector along a particular axis is what we call its component. Its component on that axis. The effective value. So although the vector is here, okay, it's not here, it's very long, but on the S axis, the length from here to here will be different from here to here. Okay. If I look at the length from here to here and here, and this is how the length of the vector is. But its effective value, okay, or how far it has gone in the east, is what we call its effective value in that direction. Okay, so here become what we call its value along the x, okay, or you can call it as the component of the vector A. How high it has also gone up becomes what we call the AY, or the vertical component, or the component of the vector A along the north direction, or its effective value along the northward direction. Okay. Okay. So look at it. A vector that starts from the origin and is directed along the customary x, y, z plane will have only one component. For example, okay, so when you say that if the vector is only moving here, okay, let's say the quantity only goes this way in x direction by a quantity of 2 units, then we are saying that if a vector D is a vector D, then which for example, if a vector D moves 2 units along the x direction, its components will read as D is equal to 0. It means that it has only a value in the x direction, it has no value in the maybe y or z direction. If you are using the 3 components x, y, z, it will become D equals 2, 0, 0. It means that on a plane like this, you have only two coordinates. But if you are talking about a space, a room, and somebody move along only one axis, see, it has no two units, but no value, it has not moved on along the x or along the y. Okay. Just imagine like a box. Okay, let me draw a box. A box. Imagine that this side is the inner part of the box. So if here is an x coordinate, and here is, let's see, the z coordinate, and here is y coordinate. If the particle moves from here only here, in the back, there is a box in the back. This side, here is the front, then here is like the back. If it moves like this, two units, okay, I would say that the displacement is 2, 0, 0. It has not moved up, it has not moved in this direction. Okay. If zero goes up like this, y or z, I can say it is 0, 0, 2. That's the displacement. If it only comes to y, I can say that it is 0, 2, 0. That becomes the component. Is okay. Now, in a situation where the particle moves maybe to the middle, okay, like this, where you can see that it has moved somehow up, somehow this way, and somehow in this direction, then you need to have x and y and z what component. How far it has moved to the x, y, and z component. Okay. So let's go. The situation where a vector is directed at an angle to the customary coordinates as is. A useful method will be employed to transfer the vector into two parts, with each part being directed along the coordinates. For example, a vector that is directed northwest can be thought of having two parts, either the northwest part and the west part. So northwest means that, let me show you northwest. So northwest. When you say northwest, it means that in between the north and the west. I think that it'll be 45 degrees, it'll be 45 degrees. That's what we call northwest. Okay. So it will have two parts, the north part and the west part. A vector with components b equals 3, 4 will have units 3. So if I see the vector has components of 3, 4 components, it's just telling the effective value in both axes. It has moved along the x axis by 3. It has moved along the y by 4. That's what we call its effective value. These are the components. We'll have units 3. Okay. Consider vector A. So I'm on page number 14. Consider vector A lying on the x, y plane and having an arbitrary angle theta with the positive x axis as shown in figure 1.2. Let's go there. Let's look at the vector. Let's see that it's a vector that is and the vector is having an angle theta. The vector that is the x plane and then the y plane is the x plane. Now, if I make a projection like this, the effective length or how far it has gone along the x direction. So let's call it ax. This is how far it has gone. Let's call it ay. Ay. So a component of a vector is effective value in a particular axis. We can see its projection in that particular word axis. Okay. So let's look there. So on page number 13, say figure 1.2, any vector A lying along x can be represented by vector A, x lying along the x, and then ay lying along. And we can see that this vector A can be equal to ax and ay. Now is to get from O to this point, you can go from A to ax direction and add ay direction. This shows the directions of how to get to like that. Okay. But this is just show the direction. It doesn't mean that the value of the magnitude of this is equal to this value plus this. This shows the direction of how to get to the vector. Just show the direction. You have to get from here to here. So you go to ax and add ay to it. That is showing the direction of how to get the way. Exactly. But if you want the magnitude of this vector, the actual length from here to here, in relation with the length from here to here, you shall come to that. You shall come to that very soon. Okay. All right. So let's quickly go back and then let's see. Now, this vector can be represented as the sum. So this vector, not the magnitude, the vector, okay, can be represented as the sum of two vectors, ax and ay. So this vector can represent not this magnitude. Okay. From figure 1.2, the three vectors form a right angle triangle. Okay, and that A is equal to AX plus AY. So in terms of the direction, okay, A equals AX plus AY direction. The vectors AS, A subscript S, and AY are also referred as component of vector A, written as AX and AY with both face, with no both face. The component AS represent the projection of A along the direction. So the projection a vector along a certain direction is what we call each component. The projection. Okay, projection is the projection of this on this axis. So we call it AY. So the component of the vector is the projection of the vector along a particular axis, or you can say it's its effective value of the vector along that axis. Is that okay? If you project this one here, then from here to this one from here to okay. That's what we call its component. And the component AY represents the projection of A along one axis. If AS points in the positive direction, positive direction, the component AS is positive. If you are here and it's pointing in negative S, it will be negative, okay, and vice versa. The same is true for components AY. Okay. Figure 1.2 and the definition of sine, cosine. From figure 1.2 and the definitions of sine and cosine. You can get cos equals AX over A. Okay. I hope you remember your trigonometries, your trigonometry. If you have a right angle triangle like this here, and the angle is here, this side is called opposite. Opposite. This side is called adjacent. Adjacent. And this side is called the hypotenuse. If the angle were to be here would have given us opposite. And here would have given us the adjacent. Where the ghetto chair, the 90 degrees faces, is our hypotenuse. Hypotenuse. Now, we use, let's say, H for hypotenuse, O for opposite, and A for adjacent. Now, there is certain acronym or mnemonics we call SOCA. SOCA, if you remember. All the basic science, basic maths. Now, the relation, if this is a right angle triangle, it only works when this is a right angle triangle. Okay, when there's a 90 degrees somewhere. The relation between the angle and this thing is that when you say so, it means the sine of the angle theta is equal to the opposite part over the hypotenuse part, each part. When we say cos or ka, that means the cosine of the angle equals adjacent part over hypotenuse part. And when we say toa means the tangent of the angle theta is equal to opposite part over the adjacent part. So if you look at cos here, the cos here, the cos theta give us the adjacent part is our AX, and the hypotenuse part is our A, vector A, the vector part. As far as the AS and AY are concerned, you see cos theta equals AX over A over A, and then this one sin theta also would have given us opposite in the Y. So the Y part is the AY over the hypotenuse, which is A. So that's what we would have gotten. Okay. So if you look at this one, this expression, let me write it here a little bit. Cos theta is equal to AX over A. It means that the AX can be equal to A cos theta. Okay, and then if you look at this place, it means AY giving us A sin theta. That is this one going here. So I can say that if the angle is attached to the axis, listen carefully. The angle of the vector is attached to the axis. The x component become ax is equal to a cos theta. Okay? If the angle is attached to the x component, the y component y, ay, is equal to a sin theta. And don't put in mind that always the x component takes cos and y component takes a no. It's based on what the angle is attached to the x axis. When the angle is attached to the x axis, that's when the x part takes cos, the y part takes sine. Okay. If the angle were to be attached to the y component, the x would have taken sine, and y would have taken cos. That would have made it. It's okay. So this one, as and ay, are components of the vector A. So vector A can be written as ax and ay. I can say the vector A, okay, A has components of A cos theta and A sin theta. Okay. Now, in terms of value, actual magnitude, then the A and AS relates by the Pythagoras formula. Very careful. The vector A is equal to AX plus AY. How to get the vector? Same as AX plus AY. The direction, there's no direction. But the actual value, the magnitude, is given by the square root of the AX squared plus AY squared. That's like Pythagoras formula, if you remember. Pythagoras is saying that if here is X and here is Y and here is Z, so that here is 20 degrees. Z squared is equal to X squared plus Y squared, so that the Z becomes the square root of X squared plus Y squared. So if you are looking for the actual value, not the direction, so you want to do this one and this one. This one is showing us the direction, how to get the A. This is showing the magnitude, the actual measurement values between the two of them or the three of them. Okay, so that is it. Okay. Now, it follows from figure 1.1. It follows from figure 1.1 that the magnitude and direction of A are related to its components through the expression. So this is the magnitude. Now, the expression here is wrong. What the expression is? What the expression is? Okay. What the expression is? We have to take tan inverse of AX by AY. That one is not correct. So we'll make a correction in your book. Okay. From this one, a tangent, tan is coming from 2. 2 means opposite the y over adjacent. Yes. So theta should actually be tan inverse of AY over AX. That should be the correct one. I think the photocopy might be an old version. The other half might be an old version. If you're having like the old version that I'm having, and then yours is having theta equals AX over AY, it is wrong. Make it the AY over AX. Rather. Some of the models have been edited long time, and then we don't have that one. You have to you have to get the latest version. If you have made the corrections. So this is how. So this side is showing us vectors and how to write the components of a vector. Okay. Now let me say this one. If the vector was going like this, okay, then of course this side we are in the negative x, region. Okay, so assuming here was 3, the x part was equal to 3, and the y part was 4. This vector would have become A is equal to maybe minus 3, 4. Or call it A because minus 3, 4. Okay. If it is going like this, if I just draw like this, I say give the vectors, the component of this vector A. We are in minus side where S is minus, but Y is positive here. So we minus 3. For that would be each component. Is that okay? Similarly, if the vector was going this way, I do this. Okay, I cut the angle to the axis. But here was 3, and then here was 4. I said, give me the components of this vector. You see that the vector A component is equal to minus 3 minus 4. Here the S is negative X, and here it is negative Y. Okay, so you have negative to differentiate from the positive X side. I get it. Let's look at so go through some of the sales assessment there. Many of them will have I think the others at the back. So you can go through them. For instance, give 3 examples each of vectors and scales. You should know. A vector of magnitude 20 units is directed with an angle of 35 due northeast. Northeast. 35 degrees due northeast. Okay. Northeast. So 35 degrees northeast, you can 35 northeast. So that is 35. And you can see that find the components of this vector. So you can either use this angle or use the angle here, 65. What you call here plus must give us 55, so that you get 90. So you can resolve it using the angle of 55. Okay, here. So look at the third one. Third one says that what? The component of a force vector is this. What is the maximum direction? So if we have a vector of components 2 and 6, 2 is positive 2, so 3, and the 6 goes up to 6. So we are finding this angle. So in terms of magnitude, the magnitude, okay, the magnitude A, yeah, magnitude becomes square root of 2 square plus 6 square. In terms of direction, you get theta equals tan inverse of the y part 6 or not 2. The angle you get, okay, becomes 6. Okay, so you can see that there's something of north of what of the east. Okay, if somebody can part this one for us, maybe assume you get 30, you can see the direction is 30 degrees north of east, north of what of the east. Okay, but the angle is okay. So we go through it, the answers are there, and then follow. Let's look at unit 1, session 4. Let's try and see if we can finish all the unit 1 today. Let's see if we can finish unit 1 today so that at least I will go to unit 2. Please, is there any question so far? Nobody has asked any question. I don't know why. Is there any question so far? Justin. Is Justin a boy or a girl? Male or female? Justin.
The place is Justin.
A boy.
A girl.
Oh, okay. All right. I hope you understand what they are saying. Are you
Yes,
following
sir.
me?
Yes, sir.
Nyomakwa. Is it Nyomakwa?
Yes, sir.
I hope you understand what they are saying.
Yes, sir.
Okay, all right. Let's quickly go through quickly so that we can see if we can finish all the unit 1. So we are in session 4. Unit vectors and law of vectors algebra. Okay, so in this session, you will be introduced to unit vectors, which are used to specify a given direction and have no other physical significance, so that it lacks both dimension and unity. They help you to write vectors in vector notation. Unit vectors also help you to identify the components of the vector with ease. At the end of this session, you should be able to define a unit vector, find a unit vector of a given vector, write a vector in the position vector notation. Okay. Now we don't. So let's look at unit 4.1. A unit vector is a vector that has a magnitude of 1, okay, and points in a particular direction. So when I say that's about magnitude of 1, let me explain. You see that okay, let's look at this one, this vector. Let's say that you have a vector 3 on 5 over 4 on 5. Let's say these are components of two vectors. Remember that we said that the magnitude of that vector give us the square root of the x component plus what the y component. Okay, that is okay. Now, so assuming I'm using this for example, this is the ax component and this is the y component. So this one will give the square root of 3 on 5 all square plus plus 4 on 5 all square. Now 3 on 5 all square would have given us 9 over 25. Okay, and give us 16 over 25. Okay, so I have square root of 9 over 25 plus 16 over 25. Now this will give me square root of, see the limiters are the same, you can just simply add the top. You can get 9 plus 16 over 25. Okay. Please excuse me.
Sir, please, you have mute yourself.
Yes, I was talking to somebody. So this one will give you square root of 25 over 25. That is square root of 1, which is 1. So in short, the vector 3 on 5 and 4 on 5 has a magnitude of 1. That's what we are saying. Okay, this is what we are saying. So when you say that a unit vector is a vector that's a magnitude of 1, it means that it's like this. The vector is like this. Okay, example it's like this. When you take its magnitude, you get 1. Okay. So a unit vector is a vector that has a magnitude of 1 and points in a particular direction. It is denoted by a U cap. Can you see that right? U cap. Then about the unit vector. You think that the magnitude of 1 the magnitude of U is 1. Unit vectors are used to specify a given direction and have no other physical significance, so that it lacks both dimensions in it. The unit vectors in the positive directions of x, y, z are represented by the ijk. Okay. The unit vectors in the positive directions of the x, y axis are represented by ijk, as shown in the figure 1.3. So, if I write ix, it means that I'm talking about a vector of magnitude 1 in the x direction. Okay, a vector of magnitude 1 in the y direction becomes the j. A vector of magnitude 1 in the z direction becomes the k. The unit vectors form a set of mutually perpendicular vectors in a right-handed coordinate system, as shown in the figure. Mathematically, a unit vector is given by the ratio of the vector to its magnitude. Okay, so if I say that, let's say this is a vector A, let's say that the vector A is 3, 4. How many complex 3, 4? What the unit vector of A? How do I unit vector of A? First, you have to the vector divided by the vector A divided by the magnitude of A. The vector A, the magnitude of A. So the magnitude of A will give us square root of 3 square plus 4 square, and square root of 9 plus 16, square root of 25, and plus 5. So the unit vector of A can be written as 3 on 5, comma, say, divided by this 4 on 5. Now come the unit vector of vector A. So unit vector A is 3. This unit vector is that you find the magnitude first and you divide the vector by the magnitude. Okay. So the magnitude is 5. I divide each component by 5. That's the unit vector. Okay. So the unit vector is just by the vector A divided by what? The magnitude of 5. Dasana, your mic is on. Do you want to say something?
No, please. It's not clear.
Which one?
The workings is not clear.
Not clear as on the board or in your eyes or in your mind. You can't see clearly or you don't understand it clearly.
Can't see from the board.
Are you sure?
Yes.
Hey,
Yes, it's not the writings are not
Please,
clear.
yes, we cannot see.
oh, I'm saying that when I am writing on the board, tap on my video and then you can see it will be enlarged.
We have done that, but we still can't see it.
Okay. So I'm saying if a vector A has components 3, 4. Can you see this one?
Yeah.
Then the
Yes,
magnitude.
sir, it's clear. You can go on. It's clear.
Oh, okay. The magnitude of A is equal to sometimes to the network can make yours scramble a little bit. So the magnitude of A is equal to the square root of 3 squared plus 4 squared. So it gives square root of 9 plus 16. And square root of 25, which is 5. So that's the magnitude of A. I want to write the using vector of A. The A cap is giving us the vector of A over its magnitude. That's what we call the unit vector. The vector of A will give us the A, which is 3 over 5. So A cap is like 3 on 5 over 4 on 5. That's what we call the unit vector of A. I get it. That's what we are saying. Okay. Okay, right. The magnitude of each unit vector, whether I, j, k, is 1. Okay. Consider the vector A lying in the xy plane. So let's look at the figure 1.4. Figure 1.4 is like this. Figure 1.4 is like this. A, and then we have A, x, I, in the x plane, and then we have A, y, j, is the y plane. So, consider vector A lying in the xy plane as shown in figure 1.4. The product of the component AX and the unit vector I is the vector AXI, okay, which lies on the x-axis. It has magnitude. The magnitude is AX. Okay. AYJ is a vector of magnitude AY lying on the earth. So if I write 3 IX, okay, 3 IX, or 4 JY, what it means is that this is a vector 3 X, okay, 3X line, or this, let's see, this is a vector 3, okay, line on the X, and the vector 4 line on the on the Y. Okay. The I and the J are unit vector. They have a value of 1. So when you multiply it by 3, it doesn't change anything. That's what I'm trying to say. Okay. Now, for the diagram, I'm reading the diagram. Figure 1.4, the vector A, normally when you write the vector A, they should put a bar at this on it. Okay, the bar doesn't come. So if you can see is A is equal to the vector between A is equal to the vector A, okay, or the magnitude. Normally write the vector as 100. Vector A can be equal to 3 or A xi plus the A Y what J A Y J. Just as we wrote that the vector A, somebody's hand is up. Mauli,
Please,
a minute. Somebody has taken my a minute. Yes, Mauli.
please, I think we cannot see what you are now writing under the board.
Okay.
The down there. I
Down
think the
there.
camera cannot capture it.
The down part.
Yeah.
Okay. I'm coming. Can you sit down a little bit? Well, I should leave the camera up, so I was bring it down. I don't know what to do. I should have the camera more down. But so we are saying that the vector. Oh, let me clean this one. The vector going like this. A. Well, we have A X I in the direction, and then we have A G Y in the direction. We are saying that the vector A, I'm writing as A X I plus A G Y. Just like we wrote that the vector A is equal to AX plus AY. You can multiply it by the unit vector. It doesn't change anything. Just that I just tell you that it's a value 1 in the X direction. To multiply the magnitude of AX by I, you just get the same as the AX. Okay, but it's just telling us that it's in the X direction. The J constant is in the Y direction, and the K signifies that it is in the Z direction. Is okay. All right. Okay. So a new vector notation of the vector A then is this. So you can write this A in this term of new vector notation. AI, when the I comes in, you have written it in new vector what? Notation. Okay. It's not anything. Now, if look at the next diagram, figure 1.5. If a point lies in the SY plane with Cartesian coordinates SY as shown in figure 1.5, it's me what I'm saying that manage to get your hard copies. Okay, so as I'm teaching, I don't like teaching this one with the laptop because of the numerous work examples you have to do. Okay, so let you understand. Okay, so get a hard copy, and then once you are going to, you also be looking at the board and to be going very fast. Okay. If I use the laptop, I'll not be able to draw more diagrams and more explanations as I used to. I'll just be referring to the material, okay, but no other further diagram explanations. Okay, so let's command it to get a hard copy, and as I refer, you also refer. So let me draw a diagram here. It says that if there is a vector on the OX, y plane going like this, y going like this, and here's R, and then XY. So that if a point lies in the XY with the Cartesian coordinates X and Y as shown in the table, then its position vector R in unit vector form is given by R. In the point lies this way. I think the point is along the side. So the R is equal to XI plus Y what J. That's what I'm trying to say. it has gone the x part, it has gone the y part. So writing the position vector and the unit vector from just main I, J, and K to their respective components in that particular direction. Okay. Equation 1.6 tells us that the components of R are the length x and y. If you want to add vectors A and B in component form so that the resultant is A plus B, then A can be equal to AXI plus this and this. Okay, so what is trying to say that? Assuming that you have two vectors, there is an A is equals to AXI plus, let's say, AYJ. There's another vector B, which is BXI plus BYJ. And you want to perform a vector addition. You want to add these two vectors, that A plus B, so that you can get a resultant. Then it's just simply adding their respective. I goes with I and J goes with what? With J. So the respective or the resultant, okay, resultant will give us this practice. So AXI plus BXI without with a plus, then it goes to the other one, B. Okay, let's pick the vector, the whole vector first. What it does that, let's pick the whole vector first. We want to perform A plus B to get the resultant. So it just becomes the vector A. The vector A becomes, okay, the vector A becomes AXI plus AYJ. The vector B, which is BXI plus BYJ. And when you're adding X, the I and I goes hand in hand. Okay, so you get AXI plus BXI, and then you have the AYJ plus BYJ. So you can then factorize, and then this gives us, so there it's supposed to be the R part, okay, they've written there R, okay, R is supposed to be AX plus BX to bracket I plus AY plus BY into bracket J. I think the subscript didn't come. Okay. In equation 1.8, equation 1.8, it didn't come. It's supposed to be AX, the X didn't come, and then BX didn't come. Okay, in the source copy. So made a correction. And here to now. So that if this vector is represented that R equals R X of I plus R Y of T, then Rx will be equal to the AX plus what? BX. Okay. And RY becomes what? AY plus what? BY. That's what it's trying to see. It's okay. That's what it's trying to see. You can represent R as RXI plus RYG, where the RS is AS plus BX, and that's what I'm trying to say. Okay. So what is mean? Just simple vector addition. Okay, vector addition. Now when you're adding two vectors, if I ask you to perform vector A is 2I plus 3J, another vector B is 3I minus 4J. I say perform the vector addition A plus B. It means that the I will add. Okay? So let's say if C is equal to this, then C become this plus this become 5I, then this plus this become minus what? 1J or minus J. That become X. That's how my I unit. I add with I and J add with J. You will add I plus J. No. I and I are adding. All the J's are adding. If they take them to, they are all added. Okay. And then if you want to find the magnitude, here, if you want to find the magnitude, then the magnitude of the vector R become the square root of Rx squared plus Ry squared. That's what it's trying to say. It's okay. and the time to time comes RY over RS. Okay. But it's not difficult. Okay. If A and B both have X, Y, Z, okay, if there's a third plane, if it's not just two coordinate system but three coordinate system, X, Y, Z, then A equals A subscript SI plus A subscript YJ plus A subscript ZK. Okay. Then if you are doing vector addition, all the IIs add, all the the JJs add, and all the ZZ also add. Is that okay? Mm-hmm. We work examples with it and you understand more. So, laws of vector algebra. If A, B, and C are vectors, and P and Q are scalars, then we have what called the commutative law of addition. A plus B is same as B plus A. Okay. So, if you have a vector A plus B is the same as B plus A, it's called the commutative law of addition. We have commutative law of multiplication. A, B is equal to B what? A. That's what the commutative law of what? Multiplication. But this is the commutative law of subtraction there. You know, it's not it's so the commutative law of addition. Okay. All right. Then you have the associative law of addition. Okay. A plus B plus C is the same as A plus B plus C. It's called the associative law of addition. So when I write, they say, what law is this? You should know. What law is this? You should know. Commutative law of addition, associative law of what? Of addition. Then we have associative law of multiplication. If P and Q are splits, like 2 times 3 times vector 8, it's the same as 3 times 2 vector 8. That's what I say. Okay. Associative law of multiplication. You can multiply this by this vector first, and before you can multiply by this. Or I can say that this can multiply with the vector first before it's multiply. It's the same thing. It's called the associative law of vector multiplication. We have 4 points. The distributive law. Okay. If P plus Q, but P and Q are scalars. Okay. Then you can have PA plus if P plus Q or the addition of the two multiply with the vector A, then you can have PA plus QA. Okay. Or if P is a scalar multiplying addition of two vectors. Okay, you can also have PA plus or PB. It's called the distributive law. Distributive law. Okay, so you must know each of them. If I write this one, what law is this? You know, commutative law of vector addition, distributive law of this. Note that in this laws, only multiplication of vector by one or more scalars is defined. All right. Let's look at how we answer example 1.2. 1.2. 1.2. Example 1.2. So that a 5 Newton force is acted on by a 5 Newton force acts on a body, okay, at an angle of 30 degrees to the horizontal. Okay. Find the component of the force. So let's say this is a body, and it's acted upon by 5 Newton force at an angle of 30. Say that find the components of the force F. The force F. Per the angle, this is the body, per the angle, this force has a y component and has an s component this way. Let's call it one F y, let's call it Fx. So in this case, we will say that it will also be that the force is acting on it this way. Also, by say that this. Let's make it this way. It's acting on it. Either it can be pulling it or pushing it. Okay. Let's say that this component is called Fx. It's called Fy. Now, if you want to find this part, this is the adjacent as far as the angle is concerned. then the hypotenuse. So the angle this side, I want to talk about this force, and this force F is hypotenuse. How adjusted the hypotenuse? How adjusted the hypotenuse? That is K. It means that the cos of the angle 30 equal to adjacent part, which is the fx part, over the force part F. So the F part becomes F cos 30. But the F is the force 5. So the 5 equals what? 30. So the Fx part is 5 cos what? 30. Now cos 30, cos 30 is 0. Cos 30 is 0.866. Okay. So you multiply 5 by cos 30, you get 4.33. So the Fx component is this. And then the y component, this component, will give us sine. Fy will give us F sine 30, which is 5 sine 30. 5 sine 30 is 0.5 times 5 gives us 2.5. So you say that the component are that the Fx component is 4.33, and then y component is 2.5. Here's how you find the component of the force F. Then write F in the position vector notation. Position vector notation, you feel that the F is equal to 4.33 R is in the S part. Because position vector notation that if you have that F equals Fx times I plus Fy times G. But the Fx is the 4.33. We don't bring S in it because the Fx part is the 4.33 plus 2.5 for G equal for the position vector notation. Then find the mean vector of F. If F is this, F is this, the mean vector of F cap, given by the vector F divided by the magnitude of F. We must first find the magnitude of F. The magnitude of F is the 5. In fact, it's coming from this square 4.33 square plus 2.5 square. That will give us the 5. So the position of the position of this one, that's the 5 they give us in the question. So the position that will give us the 4.33 I on 5 plus 2.5 G on what? 5. That's the F for the position vector what? Notation. So 4.33 G I plus 2.5 G. That will give us for the position vector notation. Okay. That's for the unit vector. I get it. You look at it. Given the vector A cos Pi plus 5G, find the magnitude of A and the direction of A. Okay, so how do you find the magnitude? The magnitude of A, if A is Ui plus 5G, the magnitude of A is by the square root of 2 square plus 5 square. That is 4 plus 3 by 29, which is square root of 29.
Hello, sir.
Yes. Yes, Governor.
Please say your screen, no.
Hello.
Your screen is not clear. That's why I want to alert you. But right now we have seen it.
It is raining in my area, so sometimes the weather will scramble small.
Okay. Oh, thank you, sir.
So by saying that, now give us the magnitude of A. Okay. So if I ask you to write the unit vector of A equals 2I plus 5G, this would be your magnitude. You have to get it. Okay, that one, I don't know what the value is. Okay, 5.4. If I have to write the new vector of B, A capital B plus B over 5.4 I plus 5 over 5.4 D. That's the U cap or U vector of B. Result. I guess it I find the magnitude. Then the direction. Okay. This one means that in the x, positive x, all the positive. Now go there to me, that go there by that. You are looking for this angle. You come stand in the theta, come in the all can say the tan theta, the opposite, tan is from 2, tan is opposite, get it, that's but you can come and go, tan is 5. How would you use the direction? Okay. And so it's for the bearing. If the angle is less than 90, so for the bearing, it's for the bearing of 60 points. If the angle is less than 100 rather, you can say for the bearing of 0, 6, 8, 7. Then it's not a part of the time. Go in the direction. Go in the direction. Without thinking. Let's look at this question. Example 1.4. Example 1.4. Let's look at example 1.4. Example 1.4. A particle traveled a distance of 10 kilometers from point O to point A at an angle of state this northeast. Then another 50 kilometers to a point B east. Find the position vector of OB, distance between point O and B, and the direction of point OB. So, that's from point O to point A. Not means that if they are not rather. And then let's get here at some point. So let me do what is here. 60 degrees northeast. This thing sometimes a little bit disturbing. Okay. Wait, let me see. After when just get this northeast. Yes. Not, but this piece of knot is like a digit. This piece of knots. This one, this piece of knots. If they just be on a bearing of 0.67, then you go from here. But when they say that 60 degrees east of north, the same as saying that 60 degrees east of east of north means that this one begins. The eastern part of north, 60 degrees east of north. How do you know? 60 degrees east of north. The eastern part of north, the eastern part of north is bottom part of north is east. So take this east of north. Go the north again and then take the east of it. That will be east of it. Then we have that is the northeast. The northeast. But for the book, okay, I'm going to add the book. Then student this northeast. It's a line going in this direction. Please, a minute. Just a second. My kid was crying small. So, as I was saying, let's stick to what is in your material. 60 degrees north, east, or north of east. Okay. For what material, it's making me understand that 30 degrees north, east is like 30 degrees north of east. Like this one. So that would be here. That would be a good distance. North of the east. But east of north, east of north of east. If I say 60 degrees east of north, if I go to north first, I go to the east, 60 degrees. But if I say that 60 degrees northeast, northeast here is the same as the 60 degrees of north. This one says east of north, same as northeast. But if you write that 60 degrees north, northeast here, I was thinking that this sentence said this northeast is the same as what I miss. The same as 60 degrees east of north. 60 degrees north east. North east. That's it. Because, but in the book, they are saying that from the solution that I see here, it means that the 60 degrees of east meant this way. Where is 60? Where is 60? Because, so let's stick to that. That's in the book. Because, so, he says that every model and this convention they use. Okay. So 60 degrees northeast, actually, they go like area is 60. And then go a point A. From the point O. The distance is 10 kilometers. So a particle travels a distance of 10 kilometers from point O to point A. An angle of 60 degrees northeast. Then another 50 kilometers to the point B, due north, due what east. So that one, you make a right there, and you go just make them a check. Just go this point B. So they are not asking that, and this is east. So this is the east. Okay, so this point A, this is that go there, and they are saying that, so the particle is now here at point B. So the question says that find the position vector OB. With respect to what is that of here? What is the task here? Then what again? The direction, look, the distance between point A and the actual distance. Okay? And then what the direction of vector OB? Direction, what the direction it means from here. So one, you need to find the components of O A. Okay, you start the where it's O and where it's A. What are the components you can get? Because here is 10 and here is attached to the x axis. The x component is the ax component. The ax component becomes it becomes 10 or as the magnitude of the 10, the 10 of the x is the by the and because it attached to x. The x component is spot. And the y component is take 10 times. For system is 0.5. So the area becomes 5. Forget 0.5 times 10. And this one is 0.866 times 10 equals 8.6. So the coordinate from here to here, A coordinates or OA coordinates is equals AX plus A1 in terms of coordinate system. The component system is equals 5, 8.66. Then you also go for 8, 8, but 8 is only moving in the x direction. No why? It's only moving in the x direction. So it's about 50 there. It does not move up, it does not move the x. In terms of position vector, the OA in the position is about 5i plus 8.66 days. And the position of 8 is about 50i plus 0 or okay, plus 0 days, or no d at all. We can say plus 0 days, the plus 0 days. So that if you want to find the vector O, the vector O is going from O to B. Okay, you go from O to B. You get going from O A plus A what? In terms of vector direction, but not in terms of magnitude. You will give you that the direction. The position vector of O you get to that OA is the 5 times plus 8.68 degrees. Okay, and that of the 8.68 are okay. So position of OB will give us 15 plus 20I plus 8.66 degrees. That will give you the position of B or position of vector OB. 20 plus 8.66. And the distance, or the actual distance, okay, from here to the actual distance, it will give us the square root of 20 plus 8.66. That is the actual distance. And then if you want the direction, the other direction, this B mixed with the initial O, then that's about the tan theta equals to the y part is 8.66 over 20 or theta from tan index of the 8.666 or 20. That will give you the actual direction. So about 24. It makes a bearing of 84. 23.4. This is how you can use vectors to solve a question like this. But per your model, unless you have any new material, but per your model, the 60 degrees north dash is the one is taken from you. North of this. Degrees north of this. And I was thinking typically, when you write state degrees north east, you know, you go to the north and go to the 60 degrees of the east, actually. Right. And let's stick to what you have in the model. Most of the time, they'll mark according to what is in the model. It is not in the convention that I use it. Let's use that one. Let's look at this question and let's see. Question 1.1.5. An expeditionary team in search of antiquities or antiques in the case travel net 3.6 kilometers westward, and then 3.6 southward, and 2.5 upward. So, I think it's on the problem somewhere. If you travel, I think that's and you travel 3.6 kilometers west, that will be west. And then you travel 3.9 southward. How about the great 3.9 south? Then you say that, and 25 meters upward. Upward. That's my problem. Because we just go back. I think there's something missing in this part.
Sir, hello.
Yes.
Sir, please, is a calculation that you are doing, like,
Yeah,
as you are
yeah,
saying?
yes.
Okay, I can't see. Like, I don't know if it's from my end.
Definitely from the
Yeah, Deborah is from your end. It's from your network. So
at the
just
rest,
restart.
are you seeing it?
Yes, sir, we can see. I can see my own. It's
Okay,
clear
then
from my end.
it is raining, so sometimes based on your place, it will scramble small. Are you okay?
Yes, yes, sir.
Maybe are you okay? All right. Okay. Now, please, those of you have your materials. Can you read for me the example 1.5? The sentence there, 25 meters upward.
Sir, it's the same thing we
Correct.
are also having here.
Huh?
It's the same thing we are also having here. It's 25 meters
Uh,
upward, no direction attached.
no direction.
Yeah.
If you say upward, it becomes like a person is going back or something. It doesn't make so much left. But assuming that the question didn't ask the 25 meters, okay, and then they wanted to find the direction, the position of it. You just that see here is left is O and then it's straight, and then you have found that the O going from the favor, going O the O is that is you have only X, okay, X component, okay, it's going to that going to 2.6 kilometers, okay, and then save months, and when you just become, if you go west and south, then becomes just 90. So if you want the distance here, both you have used just I can go 2.6 yeah, yes. All have given us the distance without it. But they have added an upward there, which is not clear. The question, what is the displacement vector? I think that what is the distance here, but it is not clear. Okay. The upward there doesn't make the change clear for me. So let's ignore that one until I get a clarification there. The 0.2, 0.025 they added. It's not clear. The 25 meters, if you change to kilometers, it becomes 0.025. But the upward, I don't seem to understand what is by the upward there. Upward there, it doesn't tell it. If you were going backwards, then we suffer down from the 39, you get 38 point something, and then for the but it's upward. I think there's something missing over there. There's something really missing over there. Let's look at the last one. Example 1.6. Find the sum of two vectors A and B lying on the x-axis. So you see A is bracket 2i plus 2j, and B is 2i minus 4j. All in meters. They end up on meters. So if you are adding the AB, they become 2i plus 2i. That gives us what 4i. But the j component will give us 2j minus 4j. That gives us minus 2. We get 4i minus 2j. That would have been the answer. You got it. That's the problem. You need to find the sum. If we're asking for the, to find the sum, if we're asking for the magnitude, okay, magnitude will give us the square root of the 4i plus minus 2 part square. Okay, it takes back the square, you get 4.5. Now I'll give you the magnitude and the direction. Okay. Direction also give us 27. If the angle becomes negative 27, it means that it is going to shape. Instead of 27, it's going this way. Go this way. If it's 27, then it becomes 27 degrees. So you can say that it is on the bearing of maybe 20 degrees, 20 degrees south of east, 27 degrees south of east. How do you ask the bearing? I think you have a next lesson, so we'll end here. If you want to come and control the example. So please, last Monday, my phone got spoiled from Sunday. I couldn't get it. Then somebody to try and add me to the group. I don't have the group. I'm not part of the group. So add me to the group. Okay, add my number to the group. And then Monday we are meeting. Monday we are meeting at, what time did we give last time? Was it 7 or 8?
No, we
What
said
time?
7 to 8.
7 to 8. Okay. Let's say 7 to 8. Okay, so Monday we meet at 7 to 8. We have to finish all this one. Just the first unit 2. I think so. You will finish with all this one on Monday, so that next time you look at unit 2. Okay, unit 2. Okay. All right. So that 1.7 on Monday. Bye bye.
Yeah, bye. Thank you, sir.